Here are the topics which we are going to be covering in this and upcoming videos. First, let's talk about rank of a matrix. What does it even mean? To simply put it by definition, it is the maximum number of linearly independent columns or rows present in a matrix. Independent, what do we even mean by that? Imagine a matrix. Now, this matrix has got two rows and two columns, out of which one is dependent on another one, meaning one row can be made from another one, either by simply performing any algebraic expression. As we see here, R2 is 2 times of R1. So now that you know what does independent means, let's get back to rank. Again, to summarize it, the maximum number of linearly independent rows or columns present in the matrix. Here are some of the important properties needed from exam and understanding point of view. The rank can go maximum up to the minimum number of order present, as we see here. It is 3 cross 1, meaning 1 here is smaller, so the rank can go maximum up to 1. Moving ahead, the square matrix is non-singular only if rank of A equals to n. Lastly, a matrix with rank equal to its order is called full rank matrix. A cool stuff about these matrices closed inside rectangular boxes is that these also represent the dimensions present. When we take one and plot it, it comes down to x-axis. The 2 from the second row also comes down to the x-axis. But when we look at remaining elements, they show a different story and get plotted on the second dimension, which is y-axis. So the 2 gets plotted, and then 4 gets plotted. Upon joining them, we see the similarity between these two equations, which we got when we revert them back. Now, how do I even find rank of a matrix in first place? There are mainly 3 methods to find out the matrix, first being the minor method, second being normal method, and last being echelon method. First, the minor method, which is simplest, but not that effective and useful. In this method, we try to find out the largest non-zero minor. Upon doing some calculations, we find out this matrix has minor equal to -2 and satisfies the condition. This method gets harder as the order of matrix increases. The normal form method. This one is better than the last one, but still not that good. We perform rows and column operations up till we get this order, consisting of all zeros except for the first element. Here is an example which you can look closely. At last we got the form we needed and found out rank to be 1. Now let's talk about the most effective form, which is going to be echelon form. This is the part from where questions are asked. As we have being seeing matrix from a point of vector, let's use that to understand one more thing. A vector is a combination of magnitude and direction, so if we keep the direction same and just increase or decrease the magnitude, it does not affect the actual vector. Using this, we can say, if we take up a vector and perform algebraic rules, but only in rows, and try to turn all the rows into their simplest form, it will benefit us, as arranging them by interchanging rows to get them in increasing order of zeros will give us the rank of that matrix. From this we can conclude the number of non-zero rows present is the rank of that matrix, which in this case is equal to 2.